Hey everyone, it's Mr. Canfield. Today we're going to be doing Chapter 7.3, Triangle Similarity. So this packet is going to cover the rest of the chapter. I'm going to break it up into separate videos though to make life easier for you. So I'm going to burn through this, and then you can always go back and replay parts or slow me down, whatever you need to do. So what is the difference between congruence and similarity? So congruence means exactly the same. They have the same angles and the same sides. The math word for same is congruent, but either one. Similarity, similar triangles have, or similar shapes in general, have the same angles, but their sides are proportional. Remember, proportional means like scaled up by the same amount. So are these two triangles similar? How do we know? So if we look, it's really hard to see on camera. So let me, 40, 60. 40, 60. So these triangles are both displaying a 40 and a 60-degree angle. So what's the third angle going to be in the triangles? Well, they have the same original angles. So whatever this is, it's going to have to be the same too, right? And the angles in a triangle always add up to 180, so that they add up to 100. So that's the remaining 80. So the angles all match. Now our sides here are 32, 24, and 36. And here they're 40, 30, and 45. So the way that I handle this is I look at what the scale factor is. With my calculator that I totally had with me the whole time. All right. So let's check the scale factor here. So from 32 to 40, I'll take the new divided by the old, 40 divided by 32. This was, so 32 times 1.25 gets me 40. Let's see what happens if we take 36 times 1.25. Same, we got 45, we're supposed to. If I take 24 times 1.25, oh, that's the wrong. 30. So all three sides are scaled up by 1.25. They're all scaled up by the same amount. Cool. So yeah, they have, these are similar triangles. Oh, and so we have triangle ABC and A to B to C. When I name this one, I have to name it starting with the same angle measure and go in the same order of the angles. So this would be DEF. And there's a symbol for similar, and it's like this. It's like a little worm, or it's like the top of the congruent symbol. So ABC is similar to DEF. So our first theorem that we have is called the AA similarity theorem. If two pairs of angles are congruent, then we're guaranteed the two triangles are similar. And if I was taking my own notes, if I know that that word, if that symbol means similar, then when I'm taking my notes, instead of writing the whole word similar, I actually just do a little squiggly thing to save myself some writing. But it's not really that important. So this is one of the theorems, one of the big ideas with similarity. You actually don't need to know the sides. If you know that two angles match, we're good. So like in these triangles, we have a single and a double, a single and a double. So they have a single that matches and a double that matches. Well, then what's that mean about this third angle for both of them? Well, it's gonna have to be the same. So since they have two congruent angles, A and R and B and S, why? These problems are from our book, and I'm like, you could pick any letters you want, and those are the letters you want to pick? Why are you going to talk about bake sales like that? All right, sorry for drawing attention to that. So we have two congruent angles, two sets of congruent angles, so we'd say yes, they are, by AA, similarity. Let's see, ABC has angles 40 and 55. DEF has angles 40 and 85. Are the two triangles congruent? Hold on. 40 and 55. Well, what's the third angle going to be here? 40 plus 55, take away 100. Not 100, silly. 95, take away 180. So we have 85 degrees left. Wait, 40, 85, and 55? 40, 85, and 55. So they actually have the same angles. Are the two triangles congruent? Well, to be congruent, remember, you have to have same angles and same sides, and we don't know. We don't know anything about the sides, so that is not enough info. But since the angles match, yes, they are similar by A. Okay, let's find our next similarity theorem. So, in triangle ABC, we got A is 3, and drawing pictures and coloring and writing on diagrams is so helpful for this kind of stuff. So I'm just reading these and putting them where they belong on the diagram. D is 9, E is 12, F is 18. Are they similar? So if they're similar, so I can't see the angles, but the sides should all scale up appropriately. So to get from 6 to 18, I can do 18 divided by 6 if I'm not sure. I got that it's 6 times 3 is 18. So then what's 3 times 3? 9. What's 4 times 3? 12. Since they all scale up by 3, our sides are proportional. And so the piece that that we're going to now conclude is that since these are all proportional correctly, this is called SSS similarity. And that should ring a bell. SSS should ring a bell because when we talked about congruence, like if this was 634 and 634, like if the sides all match perfectly, then we would have two congruent triangles. So when we have two SSS situations where they scale up the same for each one, or scale down the same for each one, that's SSS similarity. This sort of stuff is really important in some real world fields. When we scale things up in engineering or in manufacturing, making sure to maintain our proportions are very, very important. So let's check this one. We got 3, 4, and 5, 6, 4.5, and 7.5. So let's see, looks like AB and DE. So 4.5 divided by 3. Oh, so it's a 1.5 scale. Let's try 4 scaled up by 1.5. No, by 1.5. I typed wrong. Okay, that's scaled up right. What about 5 times 1.5? Okay, so they all scaled up right. So we call it the SSS similarity theorem. If all 3 sides have the same scale factor, then we have similar triangles. This is not the official math way to say this, but hopefully it's making sense saying I scaled up, scaled up, scaled up. They all scaled up to the side that's corresponding. So I guess I should say corresponding pairs of sides. And corresponding just means that it's like coming from the same area of the triangle, the same piece of the triangle. Okay, now we get to, for me, what are some really hard problems if you just leave it the way that it is. It says, are triangle PQS and RQP similar? PQS, RQP. Well, I kind of look at that and I lock up a little bit. So I have a recommendation when you have a diagram like this that has multiple triangles squished together. Sometimes it can be really helpful. If I'm trying to find out if these are similar, I'm just going to draw some random triangle. It's not trying to look like this. It's just a random triangle, and I'm going to label the sides P, Q, S. And then on this one, I'm going to this was P, this was Q, this was S, so then this is gonna have to be R, Q, and P. Like, I'm gonna have to follow that same order, R, Q, P. And now I'm gonna try to, let's see, from P to Q, what is that? And I go over here, P to Q is 18. Q to S, oh, Q to S is this thing here. That's 15 and 27 together. Oops, I gave the answer. I meant to say that's 15 and 12 together, it's 27. So that's from Q to S. And then do I know from P to, I don't know from P to S, okay. Let's see, do I know any of these sides? Oh, I know from R to Q is 18. Nope, that's Q to P, silly. Q to R, that's right here, that's 12, okay? Let's see, Q to P, that's 18. And then do I know R to P? I don't, okay. So the reason I took this and broke it up like this is now, instead of having to look at that and figure out which side goes with which side, now I just have these two sides go together and these two sides go together. And then, we need the third side to be able to use SSS. The third one is, wait, look at this. They have this angle Q. Look over here. Angle Q is this right here, right? So compare this angle and this angle. They're both that corner. That means this angle's the same. We have a side, an included angle, and a side. A side, an included angle, and a side. That sounds a lot like SAS. And this is going to be SAS. Let's see. So how does 18 scale to 12? I'm going to do 12 divided by 18. I got, ew. So if you push math, enter, so 2/3. So I can do 18 times 2/3 and get 12. So if I do 27 times 2/3, I get 18. Okay, so yeah, these scale appropriately. So this is SAS similarity. So I'm not gonna write the if and then. This is the situation that we have. If we have a side, the included angle, and the other side. Okay, fine. Side, included. So the side needs to be similar. The included angle needs to be congruent. And then the side needs to be similar. And the sides have to be the same scale factor. Then we're guaranteed similar triangles. Okay. So like I said, I'm flying through this, but you can always pause me and go back. Are these two triangles similar? ADE, and there's so much going on here. So ADE and then ABD. Let's see, A to D is 2.4. D to E is 1.8. And that angle in there has a single mark on it in the diagram. And then A to E is 1.8. Okay, let me see what we have here. A to B is 3.2. B to D is 2.4. And then A to D is 2.4. Okay. So are they similar? Well, I see an angle, but I don't see an angle over on this one. And ABD, I don't see any of my angles marked. But let's look at our scale factor here. How do I get from 2.4 to 3.2? 3.2 divided by 2.4, I get 1.3 repeating. Okay. What about 2.4 divided by 1.8? I get 1.3 repeating. Oh, and that's gonna be the same there too. Okay. So all three sides work. So I didn't have the angles working, but all three sides work. That actually does mean that this angle will work, even if it doesn't look like it. So by SSS similarity, these are similar triangles. What about, so I'll pause for a second. All right. What about ADE? And I'm just starting again from scratch. I know I I know I basically wrote ADE, wrote it here, but so from A to D is 2.4, D to E is 1.8, and then E to A is 1.8. What BDC? Those are my initials. Very good choice, very good choice. All right, so B to D is 2.4. B to C, we don't know. And D to C is 1.4. ADE, oh, they've got the ADE has this included angle here, and in BDC we have this included angle here. Okay, so what I need to find out is, since I have side angle side, side angle side, I need to find out, do these follow the right proportions? So 2.4 divided by 2, wait, that's the same number. So that just be 1. So this scales by 1. Does 1.8 scale by 1 to 1.4? No. That one scales by 0.7 repeating. So because of that, since they don't scale by the same amount, we don't have SAS similarity, and I don't have any other information, so these are not similar. And that is my preferred method to do those. It's tedious to write it out, but it's like the safest way to do it. All right, so here's some like legit-ish real life stuff about Avery and a radio antenna. Okay, never mind. I'm gonna eat my words almost immediately. Avery puts up a radio antenna tower in his yard. Did he buy it? Because if he bought it, it probably said on the box how tall it is. Because in the end, we want to know how tall it is, and it's like, we'll just buy it and see what it is on the thing. Anyway, so this is a situation that we run into a lot, where we have two things that are standing straight up and down, and there's the sun somewhere, and the sun is making a shadow with them, and we're so close together compared to the sun. The sun is 93 million miles away, that the angles that we're going to make with the sun are essentially the same angle, because we're so tiny and the sun is so massive. So for all intents and purposes, the sun hits there, boom, and we got a shadow. Sun hits there, boom, we got a shadow. And now we have a right angle, and this angle matches. And so because of that, we have angle similarity. We're assuming that Avery is standing perfectly straight up and down, and the tower is perfectly straight up and down. And so because of that, 5 goes to 40 and 6 goes to this. They have to work the same way. So how does 5 go to 40? Well, I can do 40 divided by 5 if you can't see it. Well, no, okay, it's 8. So then 6 times 8 will get me the result. It's 48 feet tall. And I can read the paragraph. Ella tells him that their city has a law limiting towers to 50 feet in height. How can Avery use the lengths of his shadow and the shadow of the tower to show that his tower is within the limit without directly measuring it? Oh, you know what? You know what? I was complaining. You put that tower up, instead of having to measure it, you could use this method to go, look, here's the math. It's only 48 feet tall. It's not so bad. That's what I get for complaining before I read. Never do that. I'll do it again in the same video, watch. All right. If the tower were 50 feet tall, how long would the shadow of the tower be? So if this is 50, well, remember that that was scaled up by 8 that time, but now what's it scaled up by? I gotta go from 6 to 50. So 50 divided by 6, 8.3 repeating. So let's do that times 5. So it would be 41.6 repeating, or I can do math, enter, and get 125 thirds. Ooh, okay. Feet. All right. Next one. When Esteban looks at the puddle, he sees a reflection of the top of the cactus. How tall is the cactus? So again, let's throw in some assumptions here, things we know. It says these two angles are equal to each other. That's 10 meters, that's 2.5 meters. And then we have the height here. So the height and the height are gonna be proportional as well. So 2.5 to 10, I'm gonna solve this twice. So to get there, we'll do 10 divided by 2.5. The odds times silly. 10 divided by 2.5. So it quadruples. So let's quadruple his height then. 1.5 times 4. I get 6. This is 6. And it's dealing with meters. So it's pretty tall. It's pushing 20 feet. So another way to handle this, if kind of the way that I've been talking about it, finding the scale factor and then using it, if that hasn't been working for you, the other way we could do it is say, well, this is my floor piece and my floor piece. So I could do floor piece to floor piece. So 2.5 to 10 is equal to height to height. So I did Esteban first, so I'll do Esteban's height, and then I'll do the height of the cactus. And this is called a proportion, and we use these all over the place to solve things like this. So the way that we handle this is, the fancy term for it is the means extremes property of multiplication in proportions, but all you need to know is that it's the butterfly or cross multiply. So I'm going to use the butterfly. And I'm just going to multiply across like that, so, or diagonally. So 2.5 times x is 2.5x. 10 times 1.5 is 15, and I'll divide both sides by 2.5. And I get that 15 divided by 2.5. I get 6. I get the same answer. So it's another way to do this that maybe is a little bit more mechanical and less thinking. I really like the butterfly method. That's why I call it the butterfly method. Because it makes it a little bit more fun. But and you do have to draw the butterfly. No, just kidding. All right, so that should lead you into this worksheet, reteach to build understanding, followed by additional practice. And it's just going to be a bunch of the stuff that we did today. So you'll skip this piece down here. The main thing to get from down here, we're skipping this proof, but so this is not in your packet. This is a separate page. If you're watching this in 2023. So with this, the lights turned out. I guess that's my cue to leave, right? Real quick, with this, we're not going to do this 2-column proof, but I do want to make sure that you know that we end up having a small triangle that has that angle and that angle, and a big triangle that has that angle and that angle. And so because of that, we have little triangle and big triangle are similar to each other. And that's going to come into play in the next section of our textbook. So see if you can figure this stuff out, and hope it goes well for you. Bye.